Hi, you might be wondering what you're doing here. Well, the details don't really matter, do they? I'm just glad you're here. And since you're here, let's talk about bad physics. Bad physics in movies, especially. You see, movies need some flavorful action, and bad physics is the perfect spice to get a good Rotten Tomato rating. Because if Justin Lin curses Dominic Toretto with real physics, Hollywood would be pretty depressing. I mean, come on. If Vin Diesel isn't one of the forefathers of changing physics, I don't know who else is. Alright. Let me get to the point. I picked a movie and a specific scene seen by a lot of people and liked by the community, but not talked as much. It's kind of like a Schrodinger's conversation. In the movie Final Destination 3 by James Wong, the scene Devil's Flight is a fantastic way to show how you cannot trust movies. I mean, the entire saga of Final Destination is a breeding spot for epically failed and bad physics. Whoa. Spoiler alert before we move on. This scene explains the entire movie's plot. So go watch the movie before you watch this if you want. Wendy, the main protagonist, is afraid of going on this roller coaster as the literal boogeyman is waiting for her to enter. As she boards the cart, she and other passengers experience many malfunctions and people definitely following rules. That was sarcasm, by the way. The general scene has a lot of gore in it, but I made sure all the important parts are in this one and that it's safe for work.
Are you really doing this without me?
Bad physics, alright? Yo, so like he was saying, I'm gonna figure out if that car is actually gonna go climb up that loop and stick at the top. Like, is that even possible, my guy? To even begin our investigation, we need to see what information we have on hand. Based on my research, Devil's Flight is actually based on a real roller coaster. And guess where it is? It's Canada's own. It's all the way in the west coast, over at PNE, Vancouver, BC. Sadly, it has been decommissioned and has been sold to an unknown buyer. Pity, eh? Devil's Flight was actually filmed in parts using the actual roller coaster corkscrew, parts in CGI, and little sets in green screen. So you're telling me people actually don't get chopped up in half? Okay. Legally, that was just a joke, okay? We had an agreement? Alright, so based on the real roller coaster database, yeah, I could find some information on the corkscrew, but not enough. There's other corkscrew variants made by the same engineering group, Arrow Development. They all use the same components under the patent, and we can find out information through the other ones. Luckily, I found the perfect fit, the one at Silverwood Theme Park. It's a blue corkscrew, and we have all the information in it. I'll show you. Wait. Before I show you any measurements or calculations or whatever, let me quickly show you a scene. Keep in mind, this is safe for work and there is no gore in it because I have removed it and it doesn't take any important parts out. Here you go. Ayo, like seriously? Does a roller coaster just stop in the middle like that? I mean, we can clearly see it is going at a pretty good speed. Well, that looks like a job for us to solve. Now comes the analysis part. From the database, I could gather that the coaster cart leaves the corkscrew part at 61 kilometers per hour. So it enters and leaves at the same speed, so we can say it's constant. Luckily, in the movie, we can see that the corkscrew part comes right before the loop. So we can say the initial velocity entering that loop is also 61 kilometers per hour. Believe it or not, the loop is actually pure CGI. It's not even part of the real coaster. So the director was probably encouraged to use trash physics when making this loop. Alright. Enough ranting, okay? Let's just figure out the radius of this loop in this vertical centripetal motion. You know what I'm saying? Matt, a freshman at Waterloo Mechatronics and my homeboy since grade 9 has come in clutch to show me how to find the diameter and the radius of this loop. The roller coaster circuit's length is 730 meters. Keep in mind in the movie it might be a little longer and it's a little different. But our best bet is 730 meters because we are disregarding some parts. Then we take all the track sections in that circuit and we count all of them. Yeah, all of them. Great choice, right? The total number of track sections were 474. Yeah, that's a lot. So this is how the calculation goes. We take 730 meters, which is the entire track, divided by 474 track sections. And what we get is 1.54 meters per track section. Me and Matt also came up with this program so we can count all the track sections, which will automatically divide by the total length, which we get 1.54 as well. Now that we have the length of the track section, we can figure out the circumference and the diameter, what we need to ultimately find. We take the picture of the loop and we put it on AutoCAD, and then we put a circle of best fit around it. And boom, we can figure out what's the circumference. And the circumference is 58.4 meters. Now with the equation pi d equals c, we can figure out the diameter, which would be 18.6 meters. And if we want to figure out the radius, we obviously divide by 2, which we get 9.3 meters. Alright, let's go.
Will you let me do my job?
Okay, fine, man. Okay. Alright, from what I heard, we have some concrete givens to figure out what we need to do. Let's make this make sense. To know if the roller coaster will actually stop at the top, we need to know the velocity. If the calculated velocity at the top is 0, then it means that the movie is using good physics. And if it's not 0 at the top, that means they're using bad physics and the roller coaster is still moving. As it goes to the top, it'll still come down because there's some velocity at the top. And in order to find the velocity, we're going to be using the conservation of energy equations. If we retrospectively look at the loop only, we can tell that the bottom is 0 meters and the top is the diameter, which would be 18.6 meters. This means that there is no potential energy at the bottom and only kinetic energy because we know the initial velocity at the bottom is 61 kilometers per hour. In the movie, we know that the cart stops at the top of the loop, but in theory, we need to figure out if there's actually going to be a velocity there or not. Even though it's 0 and there's only going to be potential energy at the top, we're going to consider if there's kinetic energy there to know if it's going to be a uniform circular motion or is there going to be any other velocity at top. As per the equation, we have everything we need. Let me show you. The velocity at the bottom is 61 kilometers per hour or 16.94 meters per second. The gravity is 9.8 meters per second squared, and the height, which would be the same as the diameter, would be 18.6 meters. Let's solve this. As we see, there's mass in each term, so we can simply just remove it. No need of finding it. Now we can substitute all of the information into the equation, except for velocity at top, because we need to find it. As we solve this equation and try to find the velocity at top, something seems quite fishy. Wait, is that a math error? Here's why there's a math error. You see, there's simply not enough velocity or energy at the bottom for it to even make it to the top, so it just simply rolls up and goes down. Now I kind of feel bad for the directors and for the movie in general. So let's figure out what velocity would you need at the bottom for the car to stop exactly at the top. We will be using the same equations and similar values, except for velocity at the top, we know that it's going to be 0 meters per second, and we don't know what's going to be at the bottom. So let's isolate for it. And after calculating it, we figure out that it's going to be 19.09 meters per second, or 68 kilometers per hour at the bottom. Now here comes another analysis part. As we can see, we got 68 kilometers per hour. That simply is impossible. I can tell you why. So, based on the engineering of the roller coaster itself in real life, it has to be 61 kilometers per hour. And in fact, if you can see, there's friction there, metal to metal. And it should surely be lower than 61 because of the malfunctions. And take it in, the car does not have a rotor or any engines or anything. It's purely based on the gravity or the centripetal forces in the track itself. So in conclusion, it cannot go 68 kilometers per hour. It has to be lower than 61 kilometers per hour based on that kinetic friction. But in an alternate universe, maybe it's true, you never know. Well, there you have it. We showed you that in Final Destination 3, in Devil's Flight, the roller coaster scene in the loop is not possible because there's clearly not enough velocity or energy at the bottom for it to even reach at the top. It would just come back down. And it cannot be more than 68 kilometers per hour or 61 kilometers per hour. It has to be lower because of the friction and based on how it's built. Well, I guess it's time for a victory dance. But before that, I hope you learned something. I hope you learned that movies, especially in Hollywood and even Bollywood, just have trash physics. And I hope you critique them as well. But most importantly, I hope you learned that in this scene, physics isn't really possible here. Unless until, you tweak some stuff a little bit here and there. Well, anyways, I gotta go. I'm glad you're here, and I'll see you later.